With the recent and various environmental problems that the world is facing right now, different researches were done in order to minimize the effects of these problems and prolong the life of the planet. Among the most used topics are regarding natural fillers that would make a material more cost effective and eco friendly. One of which is rice husk, which is the outer covering of a rice grain. Hi, I am Eliza Sarai Arenas, and we will talk about rice husks as reinforcing fillers in the fabrication of low-density polyethylene in the Philippines.
Rice grain is covered by an outermost layer called rice husk, also known as rice hull in some countries. During rice milling, this is usually detached and considered as waste. Rice husks are yellowish, have a convex shape, and are lightweight. With the wide production of rice in different countries such as China, Philippines, and India, a large number of rice husks is just usually stockpiled or burnt. However, since both processes may further cause environmental problems such as air pollution, different attempts to wisely utilize rice husks were made. One of which is in the fabrication of plastics, such as low-density polyethylene, propylene, and vinyl ester, which are reinforced by varying amounts of rice husk to produce eco-friendly and low-cost material, which have higher tensile and flexural strength, thus improved mechanical properties, which is to be discussed later on. In the Philippines, a power plant that runs on rice husks, also known as IPA, was activated in San Jose City, Nueva Ecija. This was called San Jose First Power Corp or SGCI Power. According to its chief executive officer, Edgardo Alfonso, SGCI Power generates a gross capacity of around 12 megawatts and feeds 10.8 megawatts to the Luzon grid by using around 330 metric tons of rice husks every day. Aside from this, the Forest Products Research and Development Institute or FPRDI of the Department of Science and Technology DOST was able to develop hollow blocks made from refined rice hull ash, sand, and cement, also known as rice hull ash cement or RHAC. They said that these are low-cost versions of the durable concrete hollow blocks. This was based on research done by Marshall Kalika of St. Louis College, who has concluded that rice husk ash, because of its high silica content, can serve as a cement binder. He also said that replacing around 10% of the cement can help save 20 pesos for each 200 peso worth of commonly used cement bags. However, these fields were only the recent developments in the utilization of rice husks in the country, with Philippines producing about 10% of the total rice meal production in Southeast Asia. It would be beneficial if other fields of rice husk utilization would be explored. The significance of the study is to conclude a method that can be done in the Philippines to produce a low-cost and durable low-density polyethylene made from one of the most abundant agricultural waste, rice husks, that may benefit the farmers, vendors, future researchers, and the environment. The main objective of the study is to examine the efficiency of using rice husks as reinforcement fillers in the fabrication of low-density polyethylene. Specifically, this study aims to observe the tensile modulus, tensile strength, and percent elongation using the universal testing machine, the hardness using Rockwell hardness test and Brinell hardness testing machine, the flexural strength and flexural modulus through the 3-point flexural test machine, and the impact strength using the pendulum impact testing machine of the low-density polyethylene sample with respect to the addition of the rice husk fillers. This study will focus on low-density polyethylene and not on high-density polyethylene and other polymers. It also focuses on rice husks as reinforcements and not the sole material in the production of the LBPE. It will also focus more on the mechanical properties of the reinforced low-density polyethylene upon application of rice husk fillers. Let's start with the chemical composition of rice husks. These may vary from sample to sample due to various reasons. This can be because of the climatic variation or difference in geographical conditions. In a study of Arjmandi, the rice husk components were enumerated into 25 to 35% cellulose, 18 to 21% hemicellulose, 26 to 31% lignin, 15 to 17% silica, 2 to 5% solubles, and 5 to 10% moisture content. It has a particle size of 26.64 micrometers, has a surface area of 0.92 square meters per grams, and a density similar to water at about 1 gram per cubic centimeters. They have also stated that natural fibers that are extracted from agricultural wastes are generally environmentally friendly, lightweight, and low cost. Thus, these are very much observed in the polymer industry. Let's now take a look at the different studies with the use of rice husk as reinforcement filler in the fabrication of plastics. In a study of Dymzowski, rice husk-filled polypropylene or PP composites were observed. It was then concluded that with the addition in the amount of rice husk, the peak stress decreased while there was an increase in the tensile and flexural modulus of the composite. This was supported by a study of Toro, concluding that rice husk fillers decreased the stiffness but improved the tensile modulus as well as the water absorption of the composite. On the other hand, Shivappa focused on the effects of rice husk reinforcement onto vinyl ester polymer composites and were able to find out that these reinforcements help increase the composite's tensile and flexural strength but unsteadily due to fluctuations. Let's now focus on the low-density polyethylene. In a classification system made by the Society of the Plastics Industry, low-density polyethylene was described as a material with good transparency, low melting point, good moisture barrier properties, stable electrical properties, has a waxy surface, and is tough and flexible, yet soft and scratched easily. In a study of Atwania, varying amounts of rice husk filler loadings 10%, 20%, 25%, 30%, and 35% weight fraction were added to recycled low-density polyethylene or RPE mixed with a 20% weight fraction of virgin polyethylene or MPE composites. The samples were then cut into specific dimensions for testing. Through the use of the universal testing machine, it was observed that there was a gradual increase of tensile strength at around 10% weight fraction addition, but experienced a sudden decrease with further percentage additions. Again, using the UTM, the tensile modulus, also known as de Young's modulus, was observed. Upon the addition of the 5% weight fraction, the previous tensile modulus of the sample, which was around 250 MPa or megapascal, became 280 megapascals, and further increased with increasing percentage additions. Through the 3-point flexural test, the flexural strength and modulus of the composites were also observed. It was found that additional percentage weights of rice husk cause increase in both flexural modulus and flexural strength. With the use of pendulum impact testing machine, it was observed that there was significant decrease in the impact value, while there is a sudden increase in the Brinell number of the composite as the weight percentage increases. They then concluded that rice husk filler loadings increased the Brinell hardness, flexural strength, and flexural modulus, as well as the tensile modulus of the composite, but decreased its impact strength and tensile strength. Lastly, according to Nuano Nenyi and Obidegu, with the incorporation of rice husk into the thermoplastic system of low-density polyethylene, enhancement was observed in the impact and stiffness behavior of the composite system, as well as on its water absorption. The produced samples were then cut into dumbbell shapes for testing. Using the universal testing machine, the tensile strength, tensile modulus, and percent elongation were observed. In testing the tensile strength, it was found out that 0% weight fraction addition of the rice husk filler. The low-density polyethylene sample has a tensile strength of around 14 megapascals, reduced to 10 megapascals upon addition of 1% weight fraction, and continuously decreased upon further addition of the filler. Likewise, inverse proportion was also observed between the percent elongation and addition of rice husk fillers. At 0% weight fraction, the LDPE sample has percent elongation at yield of around 688% and at break 789%. This then decreased at values of 534% and 688% respectively upon addition of 1% weight fraction and further decreased as well upon for further addition of the filler. On the other hand, the tensile modulus of the sample at 0% weight fraction is 5.45 megapascals and increased to 5.97 megapascals upon the addition of 1% weight fraction. This then gradually increased upon further addition of the filler. Likewise, at 0% weight fraction, the hardness of the sample was only about 40, but increased to 43 upon the addition of the 1% weight fraction. It also increased furthermore upon higher percent weight addition of the filler. In contrast with the study of Atwania, Wananenyi and Obidegu concluded that with the addition of rice husk fillers, there was a decrease in tensile strength to the polyethylene. However, both of their research showed the direct proportion of tensile modulus and hardness to the addition of rice husk fillers. Wanananyi and Obidegu also concluded that these fabricated composites can be used in domestic products and electrical housing units, where the level of water absorption and low strength of LDPE is not a critical factor. According to them, the addition of the rice husk fillers can also help reduce the material cost since wastes were used. After studying the methodologies of different researches and considering the resulting mechanical properties of the products, I have narrowed down the procedure to this experimental design, containing materials and equipments that are available in the Philippines. It is also assumed that this method would be able to produce a low-cost and durable low-density polyethylene.
Since rice is considered as staple food for the Filipinos, they are among the biggest rice consumers in the world. In line with this, the Philippines became one of the largest rice producers and brings about 3.1 million metric tons of rice husks every year, according to the Rice Technology Bulletin of 2005. Other than this, the country is also known to be one of the largest consumers of plastics. Thus, having a better way of utilizing these rice husks, specifically in the fabrication of these plastics, would make a huge difference for the country.